Yes, so I'm glad to introduce our next speaker, Ruma Maity. She's from IIT Bombay. So she's going to speak on parameter dependent current element analysis for ferropneumatic solutions.
Thank you, sir. So this talk is this work is a joint work with my supervisors, Mr. David and so here is the outline of my talk. So as the title of the talk suggests, we are going to discuss the ferropneumatic systems. So ferropneumatic system is a colloidal suspension of magnetic nanoparticles in pneumatic liquid crystal first. So we are going to briefly discuss what is liquid crystal, in particular what is pneumatic liquid crystals and ferropneumatic systems. So the model problem is the free energy of the ferropneumatic system, and it consists of small parameter that is in fact a field elastic constant. So we are interested in the asymptotic analysis of this Gaviscon elastic constant limit. So the next part is about the discrete approximation of the minimizers of this ferropneumatic energy, and there we will discuss the a priori analysis and numerical results. So liquid crystals are transitional phases between crystalline phase and liquid phase. So the constitutive molecules in crystalline phase has a regular structure where the positions are fixed in 3D lattice. But whereas in liquid state, the molecules can flow freely and they do not have any fixed rotational order. In liquid crystal state, the molecules can flow freely like in liquid, but they tend to align locally preferred orientations. So this is a optical texture of pneumatic liquid crystal sample, which is viewed under cross polarizers. So this points with emergent brushes. These are the different points in pneumatic liquid crystals. Pneumatic liquid crystals are the simplest liquid crystal phase. It is formed of rod-like particles. So coming to the applications of liquid crystals, we are very famous for their successful applications in display devices. That is in particular in LCD industry. Apart from that, there are many new research areas are coming up, which includes applications in organic electronics, where the organic materials are used for semiconductor devices, in biotechnology for biodetecting viruses, bacteria, in food science, pharmacology for the drug and nutrition elements in human cells. Pneumatic liquid crystals are anisotropy materials, and they with direction dependent responses to external electrical and optical fields. So that is what makes them a working material of choice in display industry. But their responses to external magnetic fields are relatively weak. So in 1917, Broker and Beasley suggested the inclusion of magnetic particles in pneumatic hose, which can increase the magnetic response of the colloidal suspension. So then, recently in 2013, Martins et al. Experimentally demonstrate a stable direct pneumatic system using barium hexafluoride as the magnetic nanoparticles in 5 cm crystals. So our work is motivated from these two recent works, where the authors study a model problem of a pneumatic suspension in a channel geometry as well as cyberphones. So the authors modeled this pneumatic suspension in random continuum theory. So this is a schematic of a liquid crystal cell where pneumatic suspension is sandwiched between two glass plates. So this gray part is the electrodes, indium oxide. So this is the microscopic view of this suspension. Here, these are the magnetic plates. This is the magnetic moment, and these red lines are the magnetic field. This orange lines represents the orientation of pneumatic liquid crystal. So you can see that the pneumatic liquid crystal molecules are reoriented near this magnetic plate. In Landau-Lisium theory, the state of the pneumatic liquid crystal is described by a symmetric resistance structure, which is given like this, where A is the unit vector and it represents the average molecular direction in pneumatic liquid crystals. Theta is the related angle in the plane. S is the probabilistic average of the angles between each molecule and this detector. So since we have this Q to be a symmetric resistance to first matrix, so it has only 2 degrees of freedom. So we can represent Q as a vector which has two components, Q11 and Q12. So this is the pneumatic free energy, where this first part is the reduced two-dimensional Landau-Lisium pneumatic liquid crystal free energy. Second part is the magnetic energy, and the third part is the pneumatomagnetic coupling energy. So this parameters capital K and kappa are the pneumatic and magnetic stiffness constants. This parameters A and alpha are time-dependent constants, and they are negative. This constants C and beta are positive with the dependent constants. This parameters gamma and beta are the magnetic coupling parameters. So this is the non-dimensionalized pneumatic free energy which we consider for analysis, where AB is the bulk energy density and that is defined in this way. So this small parameter A depends on pneumatic elastic constant, temperature and the domain size. So here this is the domain 0L, and after non-dimensionalizations, this scale domain has unique characteristic length. And so this chaotic bulk energy density has a parameter which is called the coupling parameter, and that is defined in this way. When this parameter is 0, the system is uncoupled. This is this energy is actually the celebrated interplanetary energy, and that is very static in the lecture. So we present the results here for C greater than 0, and the analysis for C less than 0 will also follow analogously. So let us look at the global mean measures of this bulk energy density for C greater than 0. So these are the global mean measures. This is how they look like. So this comes from the minimal condition of AB at the point psi b. So this constant QC and MC satisfies this cubic equation, and MC is given like this. So and phi is the real number. Then the detailed computation of this global mean measures can be found in this code by Dalton. Then we define this energy minimizing state, that is bulk energy minimizing state, which consists all instrument functions such that it is they are the minimizers of the global minimizers of the bulk energy density. So for the analysis, we want this bulk energy density to be positive, but that is not confirmed from this formulation. So we subtract the minimum value of this bulk energy density and construct a non-negative bulk energy AP tilde. So observe that AP tilde is 0 if and only QM is a global minimizer of AP. So instead of studying this energy functional, we replace this AP here by AP tilde, and we analyze, we consider this modified energy function in tilde. So next the admissible state. So the admissible state consists all H1 omega functions which satisfy the given directly boundary conditions. So these directly boundary conditions are chosen from this energy minimizing state of the work energy potential, and we also assume that degree of CNC. So more precisely, G will have this particular form where QB and MB are defined in this way, and phi d is a given C infinity function from del omega to R, and QB and MB have zero binding number around del omega. That is the boundary of del omega. So in the asymptotic analysis in LH2 zero level, we have this following basis. So we consider a simply connected bounded set omega such that as per its own boundary. Then the global minimizers of India will have this convergence result. So we establish that this global minimizer psi converges to this limiting function in H1 omega up to a subsequence as L tends to 0. And this limiting function will have this particular form where they're constructed using harmonic function to satisfy this given boundary data. So recall that this boundary data phi d is associated to the directly boundary data we have considered. So this is the infinite boundary test result for the absolute values of QL and the absolute value of ML. This result is not ours. So this was already available in the register and found in this work. Next, we establish this uniform convergence result in the domain interior, where we establish that modulus of QL converges to QC, and this absolute value of ML converges to QC, and this is the convergence result for the angles where QL and ML has this representation. So these results are on every compact subset and area of omega. The next result is the bound of the H2 lobe bound of this global minimizers, and this bound is independent of L. So next we extend the analysis for we analyze this near the boundary. So these are the final bases we have on the full domain omega. The first result is the bound for the gradient of the global minimizers, and we get the upper bound C by square root of L, where C depends on this boundary condition C and omega. And this uniform convergence results are on the omega bar. This is the result of this result of the normal derivatives of these global minimizers. This is the main result we expect. So the sequence style remains bounded in H2 omega, and then the bound is independent of the parameter L. So actually, this result plays an important role in the finite element analysis. So next is the discrete approximation of the energy minimizers. The energy minimizer satisfies this system of elliptic PDs, which has this cubic nonlinear term and quadratic nonlinear terms like this. So for the operator formulation, we define this bilinear form A, and which corresponds to this gradient part. This linear part is captured in this bilinear form B1. This this trilinear form corresponds to this quadratic nonlinear terms, and the cubic nonlinear terms are captured in this quadrilinear form B3. So to represent the whole system, we define this capital A, B1, B2, and B3 in terms of small a, B1, B2, and B3. So yeah, this trilinear form B2 represents all the terms here, and this is the explicit definition for that. And B3, this quadrilinear form B3 represents all this term, and this is the definition for that. And each term in the definition of B3 can be represented in terms of small b3. So the continuous nonlinear problem 6 psi in the adjacent space such that for all phi in B, this system holds. So we want to approximate the regular solution psi which satisfies the uniform bound. So recall that the previous part we have established these bounded spaces for a particular set of global minimizers. Here this is an assumption. So since we approximate the regular solution, so we have this H2 condition where D is value from DNS we find in this way. So the discrete space is the product space and X is the conforming finite element space subspace of H1 omega, which consists all continuous functions such that on each triangle this is P1 polynomial, and this triangulation is a shape regular triangulation. So then we define the space PH, which is the subspace of Xh, such that it satisfies the homogeneous boundary conditions, and therefore it is a subspace of H1 0 omega. So this is the discrete nonlinear problem, which takes size in the discrete space such that size is GH on the boundary, and for all phi's in PH, the system is satisfied. So we have considered this GH to be the P1 Lagrangian equation of G along below. These are the main results in finite dependent finite element analysis. So we considered the psi to be here the superscript A is suppressed here. So psi be a regular solution of the continuous nonlinear problem such that the uniform bound is to bound poles. Then for a fixed L greater than 0, a sufficiently small discretization parameter chosen as h to the order of L power of the sigma greater than 0, there exists, we established that there exists a unique solution psi h which approximates psi such that this energy non-convergence is of order of h, and this is the result of L non-convergence. So this part is the meta approximation error, homogeneous selective meta approximation error. This is the best approximation result, which basically says that psi is the best approximation of psi in this discrete space Xh up to this meta approximation error. So note that when G belongs to 3 by 2 del omega, this is of order of h power 3 by 2. So this is not actually optimal in that case. But when we have more regularity of G, that is when G belongs to H2 del omega, we can get improved convergence rate. So overall convergence rate will be A square. But when we have G in H3 by 2 del omega, we have only some optimal convergence rate for conforming. So for that, to improve this result, we have used Macy's method, and we get optimal convergence rates in L2 norm error as well. So the main difference between Macy's method and conforming FN is that in conforming FN, this boundary data approximation, this condition is imposed in the finite element space, whereas in Macy's method, the non-homogeneous derivative boundary data is penalized in the discrete system. So next we proceed to the numerical results. Numerical is the solution configurations of arithmetic systems are motivated from this experimental work by Sarkozy and 2007. So the author study a planar bistable magnetic liquid crystal device where the domain is a square domain 0, 0, 1, and this device has two sets of stable solutions. So this is the diagonal solution and this is the rotated solution. So in diagonal solutions, the molecules tend to align along the diagonals of the square domain. So we have two diagonal solutions, and in rotated solutions, the molecules tend to rotate in pi radian angles between two opposite edges. So we have four rotated stable solutions for this device, and also the boundary conditions here that are tangential boundary conditions. So that means if the molecules are in contact with this square edges, so they should lie on the edges, along the edges. So for the arithmetic system, we have considered a square domain 0, 0, 1, and this is the tangential boundary conditions for solution components. So this data we have taken from this paper. So note that this solution components has discontinuities at the square coordinates. So to remove that discontinuities, we construct a Lipschitz continuous boundary condition G using trapezoidal shape function. So these are the solution solution profiles for corresponding to given pneumatic stable state. So for C equals to 0, we see a magnetic vortex at the center. So, so this basically shows how the solutions of uncoupled system are perturbed by positive coupling and negative coupling. So for positive coupling, we see the co-alignment of magnetic director and the magnetization, pneumatic director and the magnetization vectors. Whereas for negative coupling, the symmetry between these two diagonally opposite plane vertices are broken, and we get two different set of solutions corresponding to this nematic diagonal solution. So these are the solution profiles for rotated solutions, and corresponding to each nematic stable states, these are the nematic solution, and the number is double when C less than 0. So this plot shows the convergence history of the solutions, the nematic solutions. So we have taken two parameters, 0 parameter values, 0.001 and 0.002. So this is for C equals to 0. So the convergence rate in L2 norm is 2 and convergence rate in H1 norm is 1. This is the plot. These are the plots for C equals to 0.25. Corresponding to V1 solution, V1 nematic stable state. This is corresponding to rotated stable state. This is corresponding to C minus 0.25. So this plot shows the convergence behavior of error for various values of this parameter L. So this is the plot for L equals to 0.01, and then keep on decreasing the values of L. And this is the plot for equals to 0.0004. So if we fix the discretization parameter value, so we see that the error here is much smaller than the error for L equals to 0.0001. So basically, we can say that the errors are sensitive to the choice of the small parameter. So this result is for C equals to 0.25, that is corresponding to the positive coupling. And this is the result. Okay, that is for the inner zero, H1 norm, and this is for L2 norm. In both cases, we see this error sensitivity. And yeah, this is the result for C equals to 0.25. We have similar plots for C equals to -0.5. That is all. So here are two references. The work I presented is from this paper.
So thanks for very nice talk. So any questions from the audience? Yeah, if you don't mind, can I start? Asking lots of questions. Yeah, so first, can you talk about, can you comment on the numerical schemes? Because it was the time state from solving the system. You have 4 equations, 4 PDs.
Yeah. We have used Newton's method, Newton's method for the linearization. The linearization system that we solve it.
So what kind of time stepping and how you solve each time step?
Oh, it is time independent.
Time dependent. So you just use only the given sum.
Yes.
Okay. So the second question is,
Yeah, there are time dependent versions of this which are interesting. The learner studies them. The question is valid, that is sometimes to figure out.
yeah. So what kind of linear solver did you use for the Newton scheme?
I haven't used any practice. Used
We wrote the code.
So initial test.
yeah, initial guess is yeah. So in the concept, we have not used any practice.
We have written the code.
Yeah.
Then what kind of solver did you use?
That is the
But inside the linear solver, you need something, right?
yeah, it's simply
The boss.
cross information.
So how many iterations you have? That's
So,
why we use question.
Yeah, for the So it depends on the size of the initial case and also this parameter.
In your. That's true.
Okay, this approximate like overall maximum 4 meter operations, where the 4 is for this very small value where it is 0.001. And for other mostly 3 meter operations.
Not much. Because the initial place, they are very close to.
Yeah, they are constructed in a particular way. So we have these tangential boundary conditions. So what I basically is that. Yeah. So
Maybe you can go back to the slide.
yeah. So for these diagonal solutions, let us look at this diagonal solution. So we take this theta values to be, we want the molecular orientation to be this way and this way, and from here this way and this way. So we take this theta value. So this Q tension has this particular form that is so if we it's basically writing it is like S cos theta S sin theta. So once we have the theta values and once we have this S value, so we can construct the initial case. So theta is the theta is the angle between this director and the plate. So this plots are the director plots only, not the individual molecules. That is the average orientation. Yeah. So for let's say B1 solution, so we take this theta value to be 0 and this case, then here we take theta value to be pi by 2 and we get the orientation like this. And similarly here we take theta value pi by 2 and theta value is 0 here. So we get this orientation like this on the boundary and by after solving the system we get this solution for the orientations like this.
So I can comment to your question. So the whole aim was to see whether the scheme is working and giving the right solutions and the right expected convergence rates. So there is a lot of scope of improvement for improving the basically the computational performance, which we haven't focused on.
No, because I was interested in this B3 is very long.
Yeah.
So let me take it. So because the coupler system and it's very long.
Yeah, so the method proposed is working. We have the scheme, but if you say you ask me to the scheme, etc., the numerator we can make it better in terms of storage and reading.
The second question is B3, I mean, your analysis. So is H1 is enough or you need something else, right? So
This where so this convergence analysis for H2 regular solution. So admissible state is subset of.
So that is fine, that was the last one, the red color, the B3. Yeah, because in
Okay, that is why is it finite? I mean, if we have an H1, we are in omega subset of R squared, and then H1 omega is embedded in T for all p greater than 1, and so it is like a polynomial, so we can do that this is finite. So we can define this for H1.
When B is equal to embedding, we say.
there are three greater than 1 or why it is 1 because we have a square.
P, I mean, that is true for all p greater than 1. So this is like we use Cauchy-Schwarz inequality. So for like here we get U1 Q phi 1. So we can get U1 power 6 and L6 norm then L2 norm phi 1. So L6 norm is finite or that also phi 1. I mean L2 norm phi 1 is finite. So that is finite.
So probably you need L6 because your cubic knowledge is there.
Yeah.
So in 3 dimensions, 6. In 2 dimensions,
Yeah, this embedding result is for that.
nope.
You said somewhere that this is suboptimal. I just want to comment on that.
Yeah, that convergence state.
It's suboptimal because the x minus half just dominated by L2 and getting 3 by 2. Get the polynomial degree 1 you are using. Polynomial degree 2 you use then G minus G H in H minus half, you can get improvement. But 100 degree what it is not going to do.
But we have G and X that will.
Yeah, G is H2 means what? Solution is going to be 2 plus half. You are assuming higher regularity.
Yeah. So that then we can do this. That's what.
Yeah, that's fine.
Oh, so any further questions? The last question is. Start right. Yeah.
Could you go to that slide where you said the errors are sensitive to the parameters?
Okay.
Okay. So this error, what exactly are you calculating? This error means isn't the difference between this QLML and the Q naught and naught?
Oh, okay. That's the question. So we do not have exact solution. So we compare the consecutive two iterations.
It's not, see, because in the beginning you said you have a parameter L, and as L goes to 0, it's the QLML that approaches on Q naught and naught, which is given in terms of exponential and so on, right? So, is it this error, what are they the error between QL and Q naught and ML and M naught?
No.
You don't. Okay, so then my question is like, see, when you have a derivative area, like L going to 0, how do you make sure that your errors are independent?
Okay. So
Yes.
yeah, we do not have reason.
I will give you a suggestion on that. What do you do? You see L tending to 0. That's a parameter. You have to take that parameter into consideration. So norm you
Yeah, now we
do weighted norm.
Yeah.
Some
then-
kind of weighted norm, you may get something.
Yeah.
When you need uniform error estimate, it depends on the whereas the real estimates are with L.
Yeah, but you get the perhaps gradient norm. The other one is not.
So
You
that
are not sick.
now we have L. So that way we can suppress that L dependence there. That
It's
may
not
be a
not
possibility.
If you take a L, then we will this kind of behavior we can expect, unless you get anything from this.
Yeah, maybe.
Might be interesting to see if you have a uniform bound independent of L, and then maybe it might be possible to show that your numerical solution indeed converges to a numerical scheme approximating this Q naught and naught.
That may be possible for that particular set of examples, for a particular set of examples. The examples we have taken is not actually, follow that conversion space and form.
Can you show the where L comes? Just one minute.
No.
L. The L parameter where it comes. It is coming not in H1 now. Yes. So, it is coming below. Yeah, oh my God. Then it is going to be thrown out to H1 now. L2 norm you can find out where is something can be done. But you can inform, your experiment says, except last part, inform norm perhaps can be okay.
Then one can pass to the limit, even in the numerical scheme.
Yeah, but
Yeah, that is for this
Not
example,
for
I
error
don't think that is
Convergence
possible.
and not order.
Sorry,
It's convergence and not order.
not order.
Yeah.
Order can be quite erratic with respect to L. It can,
So we are getting, we are focusing on order. Right? We are focusing on order. The estimates is right. So convergence is possible.
uniform with respect to L.
This question goes to 0.
Yeah, when it goes to 0, then that errors cannot also
Real
integrate.
pattern.
If you are not bothered about the, then you use the LH2 approach and get probably show that.
That is this kind of stiff the problem getting uniform error pattern. This two bit games if L goes to 0.
I have a feeling,
No,
the norm consisting of the gradient plus L2 norm, the gradient will not L2 like your singular product. So therefore, something can be done. Because how numerical explain series, except for the last one, is almost uniform linear. So it is infinite somewhere. And more, if you take discrete solution, and perhaps you can call that way.
probably, sorry, probably
Not for the other.
Let's start the speaker again. So now we move to the LH2. Huh? There's one more. There's one more.
Oh, is where?
LH1.
Oh, I thought it was fine.
No, there's one.
Yeah. That can.
The wisdom there is no one talking about it. And